Hello guys, so welcome back to our VHDL lessons. So in today's lesson, we're gonna explore the design of half adder. It's really simple design, but it's a base, as we said, or a foundation for more complicated designs in the future. Like for example, the full adder. Okay. So here on the right, we see the truth table of the half adder. Here is a carry, here is a sum, and then it's basically the equations that we get from the Karnoff map. So if we express this in a Karnoff map, just a 2 by 2 Karnoff map, then we get these two equations. That C is just the ending of the two inputs, and the sum is the XOR between them, just like this. And remember, we can code XOR in VHDL just by using XOR, which is a default representation for the XOR gate. And you can of course do it using two AND gates and an OR. And here is the implementation of the C. Okay, so here is the implementation in VHDL. It's really very simple example. So we have two inputs. We have the two outputs, the carry and the sum, and both of course are standard logic. Okay. So then we build the architecture. This is a behavioral architecture or behavioral design. And here is the name of our entity of our design, which is half adder. And here is the first output, and here is the second output. And one note to note here is that in VHDL, this is called combinational logic design. Okay. And in combinational logic design, the order doesn't matter. Okay, so we can write, for example, this sentence before the sentence or after it. That doesn't matter at all. Okay, and this is basically what happened in hardware. So hardware is a concurrent, should be concurrent all the time. So combinational logic hardware should be concurrent. So it doesn't matter if this is before this or this is after this. Okay. And this is again come from the combinational logic physics. So here is, for example, this circuit here. When we add X and Y, I mean, when we apply X and Y at these two inputs, okay, S and C will appear just after the delay of the XOR and the delay of the AND. So it really depends on the AND and XOR delay. It doesn't depend on the which is before which in the coding. Okay, and that's basically why it is a concurrent modeling. So let's compile. Okay, now the compile is successful. Now let's simulate this. I have here the test bench for it. Okay, so again, the test bench is just a template, the test bench file, just a template that looks like a new design because it has entity, although it's empty, because basically you are using this template to simulate another design, which is in our case a half adder. You also should build an architecture for it, which is basically signals that takes values. Here you define or instantiate the component of the design that you want to simulate, which is the half adder. And this is basically the same entity as here. Okay, I'm sorry, this is the entity here. Okay, then after that you instantiate signals which will be connected to the inputs and the outputs. So the number of signals here should be at least equal to the number of inputs plus the number of outputs. Then you connect these signals to the inputs and outputs. So X, N, Y, N is connected to X and Y. Then C and S is connected to S and C. And again, the naming doesn't matter. You can name this signal here with whatever name you want. And what matters here is the order here. So look at the order here. So X first, then Y, then C, then S. Then whatever you write here, this will be the connection. I mean, whatever you write here in the first place will be connected to X. Whatever you write here in the second place will be connected to Y. The third place will be connected to C, the carry. Then the final one will be connected to the sum, based on the orders that you have here. Okay, Afterwards, we put values for x and y and check the output. Okay, so in our case here we have two inputs, so you can write easily the four combinations. And again, you can start from, again, the order here doesn't matter. So let's order them just to make it more clear for us, or more traceable, we can say. So let's start by the 0, 0, then 0, 1. We have it also here. Then 1, 0, then 1, 1. Okay, and you can, leave this last input, or you can just make a kind of clearance. So this will be the default after 4 nanoseconds. Okay, and we save that. So let's compile now, and we should see no errors. Good. Now we simulate. We start simulation. We go to work, and we choose our test bench. It's ordered or sorted by alphabetical, so it should be go a little bit down. Yes, half other test bench. Okay, and here is the simulation panel. First, we move our signals to here. And now we need 4 nanoseconds here, so we need to test to zoom out a little bit. Here we have 4 more than, so let's now simulate. So when x is 0 and y is 0, both the carry and s are zeros. Then when x is 0 and y is 1, the carry is 0 and the sum is 1. This situation here. Then when x now is 1, y is 0, this situation, we have carry is 0 and the sum is 1. Then finally, when both are 1s, we have the carry now is 1 and the sum is 0, which is basically 2. So the overall result, don't differentiate between the S and C. The S and C together, concatenated, are just your result. So this is basically, the design. If we continue, of course, we're gonna reach the default, or the last, state here, which is 0, 0, and 0, 0 will give you again 0 and 0. Okay, guys, so that was, the half adder. It's really easy. In the next video, we're gonna build a package out of this half adder, then use it in another design, which is the full adder. Okay, thank you very much for watching this, and see you in the next video. Bye-bye.